Okay. So variation is an important concept because especially when we're dealing with things like human beings, which are a complex organism, in that we expect that there be good variability between not only groups but individuals. Variability is what makes it so an organism can adapt to environmental changes, but it also provides us with an idea that there are differences within a group and there's differences between a group, and it's all due to how variable the individuals in that group are. From our demonstration last Thursday, you remember where I overlapped those two groups, and we put, I believe we were measuring femininity to masculinity, and we could see that there can be average differences between males and females. But when we overlap the distribution, we see that due to the variation within those two populations, there's a great amount of overlap between the two genders when it comes to measuring masculinity and femininity, that there's a great number of overlap. And that's why we can say there's probably more similar. We can, if you actually look at those distributions, there is actually more variability within a gender than there is between a gender. And that's the important things that variability can tell us is really how many people actually differ from each other and by how much. Within a single population, we can see how much people differ within a single population, how much scores vary, okay? So let's go on with some formal definitions. Okay. So variability, the goal of variability is to obtain a measure of the spread, how spread out scores are within a distribution. A measure of variability usually accompanies a measure of central tendency. As we described last week, we usually use mean, median, and mode to describe those things. And so if we just look at central tendency, as we described last week, central tendency describes a central point of the distribution, denoted by a mean or a median, and describes how the scores are scattered around a central point. Together, central tendency and variability are two primary values that are used to describe a distribution, okay? Pretty much when we get into inferential statistics, mean and standard deviation will be the main numbers that we will need when we're calculating many of the statistics that we'll be using. When we're talking about descriptive statistics, we'll use more than just mean and standard deviations. We'll use things like range, mode, median. But just so you know, a lot of what I really would like you to understand is the mean and the standard deviation component. Because when we get into inferential statistics, those will be the two main measures that we're going to use when we're testing differences and similarities between two groups, okay? Variability serves both as a descriptive measure, as I just explained. So we use it to describe the data, the spread of the data. But again, it's an important component to when we get to inferential statistics. So you know, when we're using it descriptively, the variability measures the degree to which scores are spread out or clustered together in a distribution. That's the use in descriptive statistics. When we're looking at inferential statistics, we want to know if the variability within our sample can represent an entire population. And so we'll get into that when we get into inferential statistics. We want to see if the sample standard deviation and the sample mean, if those, how much those represent the population from where the sample came from, okay? When the population variability is small, all the scores are clustered close together, and any individual score in a sample will necessarily provide a good representation of the entire set. When we look at, so when scores are really close, the variability is really small, what we'll see in our bell curve is we'll do this, and if variability is small, the bell curve will look more like a slim bell than it will a spread out bell. So it'll look something like this. So that shows how with a small variability, what it's like. When we have large variability, we'll see our distribution look something more like this, more like the graph we looked at the other day, where it will be more out, okay? So that's the difference between when we're looking at the distribution, what the large spread of scores would do, and the like. Now, the thing that we have to check for when we're looking at well, let's get to that later. What I'm going to say for right now is that when we're looking at variability and when we're looking for standard deviations, the biggest influence on standard deviations and the mean really is what we call outliers. And those are scores that that are outside the range of the normal scores. And I'll show you statistically how we control for outliers, because not all outliers are bad and they can help represent our population. But we'll show you when we get to the section, when we start cleaning data, we'll look for what are called outliers. There are three basic types of variability. One is range. The second is interquartile range. And then the big one is standard deviation and variance, okay? In any of these cases, what we're really measuring is distance. When we're measuring range, we want to know the total range of the score. So if we were to figure range for, let's say, okay, let's just say for this number, this would be represented, the range would be 5.12. It also can be represented, so sometimes range is written with the smallest number, 2 dots, and the largest number, or range can be represented by subtracting 12, the highest number from the lowest number. So the lowest number is 5, the highest number is 12. So 12 minus 5 equals 7. So this has a range of 7. Now, the reason why there's these two representations, and sometimes they'll do 5.12 and then in brackets they'll put 7. The reason why we want to know this is so that we know the value of the smallest score, the value of the highest score, and then of course how the spread. So this is smallest score, highest score, and the spread between these two is 7. So that's how we calculate range, okay? Now interquartile range and standard deviation we'll get to here in just a minute, because there's some slides on those, but this is basically how we calculate at least the range as of right now, okay? All right, so range, as discussed, covers the distribution from the highest score to the lowest score using the upper and lower real limits of the range. So for this example, the real limit of this is 5, lower limit, the highest real limit is 12. And that's really what they mean when you see in statistics, the real limit. What we're looking for is the actual numbers. Now, again, when we get into inferential statistics and stuff, we're going to have what's called confidence intervals, which will adjust the real range. But when we're looking at this just from seeing the variation within our sample, we just call this the real limit. We use the real numbers when we're, especially when we're using this for descriptive purposes. Interquartile range is when we're trying to find the how many individuals are within a certain range. So I think there's a slide on this. No, hold on. Okay, so Q1 you can say is 25%. So at Q1, what Q1 will tell you is how many individuals scored below 25. How many people scored below 25% and how many scored above 25%. In Q3, we want to know how many individuals within a distribution scored 75% below a given score or above 75% in a given score. Okay, so what this relates to, if we look at this, okay, this interquartile range, we have 25% here, which would be Q1. So we know that, so this is at 4.5. What this says is that 25% of people scored below 4.5 on this given test, okay? Now, this is 25%. Okay. And then we have another 25%. No, we don't. No, we don't. I lied about that. We have 50% that scored between 4.5 and 8. Okay. And our mean would go right down the middle of this. All right. And then in the third quartile, we see that 75% of people scored below 8, and then that would make 25% scored above 8. Okay, so that's what quartile range is for. We usually use this type of statistics when we develop a measure. So you know, when you take your infant to the doctor and they do the body mass measures and all of those things, and it looks like a chart that has all these lines on it, and basically it's using this system where you have age listed right here, right? And then you're going to have the average or the mean. And then they usually have your 75% up here, your 25% down here. And then for sakes of measurement, they'll also add other quartiles to this once they've figured these 3 basic ones out. Okay, and so that's kind of that chart, that growth chart that you see in the doctor's office. This is what these are the statistics that are used to determine those things. Okay, so that's quartile range and how that works. Okay, standard deviation is the standard distance between a score and a mean. Okay, so whenever we have a mean, the standard deviation, an individual score, is the distance. The standard deviation is the distance between that mean and that score. And in the end, what it gives us is the average distance between individual scores. Okay. So, but remember this calculation of standard deviation. Whoops, not this one. Sorry. Standard deviation is the measure of the distance between a score and the mean. Okay. This is basically how you calculate a standard deviation. And we'll go through this. Actually, you know what? I think it would be easier. Let's watch the video. So let me stop sharing this for now. I want you to watch the video on how to calculate a standard deviation. Let's go through and look at an applied example of how to calculate the standard deviation, and then we'll go through the equations, okay?
Hello and welcome to My Secret Math Tutor. In this video, we're going to calculate the standard deviation. Now, when calculating a quantity like this, it's good to note that depending on whether your data comes from a sample or a population, there are actually two different formulas that you have to keep track of. And they're almost identical, except for you'll notice in the bottom here, in the sample, it has an n-1, whereas when you're dealing with the population, you really just have a couple of n's, or an n squared. All right? So you do have to know exactly what your data is coming from, but other than that, it's a fairly straightforward and simple calculation. So let's go ahead and move on to an example and see exactly how this would work. So here I have just a bunch of different data points, and I'm going to assume that these are all from a sample of some sort. And we're going to need to find these various different pieces of the formula and plug them in. One of the pieces we'll need to find is this n, and that simply stands for how many data points do you have. So if we just count these up real quick, I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 different data points, so we know that n is equal to 10. All right, moving on. We can see that this is the sum of all of the values of x squared. So there's actually two things we need to do. First, we need to find all of the values squared, and then we'll add those up. Now, this can take a little bit of time, and it's probably a good idea that you have a calculator to take care of these individual steps. I'm going to use my calculator and quickly move through these. All right, so I've gone through each of our data points. I've squared each of them, and now we need to take the total. So again, using a calculator, we could just add all of these up. In doing so, I get 8, 5, 5, 1, 1. So this represents the sum of all of the x values squared. Now, it's not the only sum we need to take. Over here, we also need to sum the regular x values and then square that sum. So again, we'll need to add these and then square that result. Adding these ones up, we get 891. This needs to be squared. So squaring 891, that would give us 793,881. All right, just to be clear what values we have found here, let's go ahead and write that with the other stuff up here. So I have the sum of the x squareds. That was 85511. And then we added up all of the values as they were, and then squared that sum. This was 793,881. Okay. So now that we have all of our various pieces, now we literally just put it into the formula. So here we're taking the square root of 10 multiplied by 85511 minus, now we have all of this stuff, 793,881. All this will need to be divided by 10 multiplied by 9. Now there's a lot of stuff in there, but it does simplify fairly nicely. Again, you might want to use a calculator to just take care of a lot of those calculations on the inside. In doing so, I get about 680.3222, and that 2 is repeating on the end. No worries. You can easily take the square root of that. This will give you 26.08 and some change. So maybe we'll say this is approximate. All right. Now, if your data comes from a population, this will be almost identical. Let's go ahead and plug those in and see what they would look like. The value then would still be the same. Same thing for our sigma x squared. So there's our 85511 minus 793881. And the change is, instead of saying 10 times 9, this would really be just 10 times 10, or 100. So now we'll need to take the square root of all of that. Even though it is a small change, you will get some different numbers here. So now this will take the square root of 612.29. And taking the square root of that, we get 24.74. And again, some more decimals, so we'll go ahead and say about 24.74. And there you go. That is the value of your standard deviation if it comes from a sample, and the value of your standard deviation if it comes from a population. If you'd like to see some more videos, definitely visit mysecretmathtutor.com.
So I wanted to start with that video just so you can see it being worked down and see how it works mathematically. But now let's go over the components of the standard deviation. So in the example that was provided, it mentioned that there's two types of standard deviation. One is the population standard deviation, which means that what you did is you sampled the entire population of a group of interest, meaning that there has been no one excluded. And so that a place where you would use a population standard deviation is, let's say, so you have a quiz that'll be due Sunday at midnight. And so since you are the population of the summer math 225 class, if I wanted to see the variation between your quiz scores, I would use this, this equation. If, however, let's say I wanted to estimate what the if I wanted to know what the standard deviation, let's say I wanted to know what the standard deviation of all math 225 classes for the past 4 years. Maybe what I'll do is I'll do a random sample of all those classes, and then I would use this sample one as the equation that I would. Okay, but let's break down these equations. This mu, it's called UM, stands for the population mean. This S, and this should be S, this should be SD when you write it out. SD stands for sample standard deviation, okay? X stands for any given value that needs to go into the equation, okay? This, I'm trying to remember what it's called, this U with a little thing on the bottom. I'm sorry, I'll get the proper name. This is the population mean. And X with a little bar over it stands for sample mean. We use an uppercase N when we we observe the entire population, and we use a smaller case N when we have the sample population. Okay. Now let's look at the equation. What it's asking for is this means sum. Now this equation looks a little bit different, okay, because this is the theoretical equation, okay? But what basically we're looking for is the sum of the sample scores minus this mean, because remember, we're trying to find the distance between individual scores and the mean. So we'll subtract those, and then we're going to square them. Okay. What square means is we're going to multiply a value by itself. So let's say in this value, if we were to calculate this, it would come out to 25. Okay. What we would do in this case, when we square it, we take 25 multiplied by 25, which equals, I don't have my calculator. Oops. 25, which equals 625. And that's what squaring means, okay? So this is square. Okay. Now this one, and I won't write the square out on this, this is the square root, okay? So when we're doing this equation, we figured this part out as it showed in the video, okay? And we use those the mathematical equation to make this a little easier. We square it and then we divide it by the total number of samples or observations. And then we square root it, okay? What square rooting is, a square root is when a number multiplied by a number to the same number, okay? So let's say the value we ended up with is 25, and we wanted to find the square root of 25. Now I will tell you, just use your calculator on this. All calculators, I know that most all calculators have a square root. If not, you can easily in Google, if you just wanted to Google square root of 25, it'll give you that answer. So but you know, so what is a number by itself that equals 25? Well, the square root of 25 is 5, because 5 times 5 equals 25. Okay. So now, why is squaring and then dividing by the total number of observation and then taking the square root of that, why is that necessary? Okay. Because if we don't square this number and we sum up the total number of scores minus the mean, we will end up with 0. Okay. It's necessary to square it so we actually end up with a value that then can be used to determine a variation. Okay. So we do that, we divide it by n, but you'll notice that that's going to end up still being a really big number, okay? Like in this example, 625. So we take the square root of that, which, okay, in this case, it's going to be 25, okay, to give us a smaller, more usable number. Okay, so the whole purpose of squaring and then taking the square root in the end is so we don't end up with a value of 0. All right, so keep that in mind. Now, again, we have two types of standard deviations, population versus sample. So what is the difference between the sample? It is this here, this concept right here, okay? N minus 1. This denotes in the standard deviation what we call degrees of freedom. Now this concept we will go over again when we get to, I'll just FRE. We'll get to very specifically in inferential statistics, but this is the concept of degrees of freedom. If what we want when we're doing inferential statistics and what we're dealing with samples is we want our data to be able to vary. When we're dealing with our population, we don't need to worry about that. But when we're dealing with a sample and we want to see how much that sample represents the population, these scores, okay, remember that each of these numbers, this 1, 2, 3, 4, 5, represents an observation or someone's score on something. But in this one, if we were to represent the population, all those scores are fixed. But we don't know what the scores in the actual population are when we use a sample. So in this case, what we're going to do is we're going to theoretically say that, let's say this is observation 1, 2, 3, this is confusing now, 4, 5. So this line represents the observation, this line represents the scores of that observation, okay? By taking away one of the observations in a kind of a hypothetical way, it doesn't take the actual score away. What it does, it allows these numbers to vary within each other, okay? So the reason why we have n minus 1 is because when we're working with a sample, we want those scores, those observations, to be able to vary from each other. So we're going to take away an observation point so that these numbers can vary with each other. So, you know, this 2 maybe in the population is observation number 4, and observation number 4 is maybe observation number 2 in the population. And that's what degrees of freedom allows us to do, is it gives us the freedom to move those observations around, because that's what we would expect in the population, okay? All right, so we did that, all right. Gone through that. One thing, when you see the term variance, okay, that is, variance is when we have not done the square root of the equation. That's what we call, it gives us what we call the true variance point, okay? And so that's, when you see the word variance, just remember that that means that we did not square root our standard deviation yet. That's when we get down to here, okay? So let's go through some properties of the standard deviation. So some properties include, if a constant is added to every score, the distribution of standard will not change. That's why in the sample we have to use the n minus 1. Okay, if you visualize the scores in a frequency distribution histogram, then adding a constant will move each score to the entire location, and the center of the distribution will change as well. So whenever you add a variable, an observation, your standard deviation and your mean will always move, okay? So that's something to keep in mind. And that's another reason we do that degree of freedom when we do the sample standard deviation. If each score is multiplied by a constant, the standard deviation will be multiplied by that same constant, and that makes sense. And this is more mathematical terms, so that's why I'm going over it quickly, because these are things that I'm not going to ask you to do. The thing that I want you to keep in mind is that whenever you add an observation in, both your mean and your standard deviation will change. If you are given a numerical values for the mean and the standard deviation, you should be able to construct a visual image or a sketch of the distribution. Remember earlier where I did those two ones, this would be a low standard deviation, this would be a larger standard deviation when you, sorry about the drawing. And so you can really kind of sketch it out in your mind. As a general rule, about 70% of the scores, and this is the other important one, we fit it into the distribution, about 70% of the scores will fall within one standard deviation of the mean, and about 95 will fall within 2 standard deviations of the mean. And so those are also important values to keep in mind, especially when you're looking at individuals compared to a group and those types of things. All right. All right, so I went through that fairly quickly. Questions about standard deviation and variation?
Lots, but I think I'm gonna have to just go back through it and read it again or watch it again.
Yeah, it is quite a bit, Diana. I see some no questions, but I think, yes, go ahead.
I'm sorry. You stated that when we were at the population and the sample in that area, when you're rooting it down, you have to keep rooting it to the smallest number, right?
No, you only take the square root once.
Just once. Okay.
Yep. Mhm.
Okay. Thank
Yes.
you.
But that was a good question, Sherry, because I kind of confused myself when I was talking about that. So thank you. Any other questions on that? Okay. So what I would like you to do is I would like you to play around with standard deviations. So I'm going to take us to our classroom real quick. I'll turn it on student view. Okay. So down here, part of your quiz for Sunday will be actually figuring out what the standard deviation for the standard deviation, both sample population, mean, median, range for a set of values. And in this class, what I would like you to do is do what is most comfortable for you, okay? Everything in this class you will be able, well, not everything, I lied about that. There's certain things that we'll do using one of these 4 modes, but most all quizzes, I should say quizzes and whatnot, you should be able to calculate by hand. So I put that tutorial up that we just watched, but you can also use MS Excel, which is spelled wrong, and Google Sheets. And there's tutorials on how to figure out standard deviation using those both. If you are going into the sciences, if you are going to go do marketing research, business analysis, if you're going to go into the social sciences, the software that I would recommend you look at and you use, or at least you try, is what's called Art and Art Studio, or it is really just simply R. And it is a free statistical software, and it's very, very powerful. And most businesses and business consulting organizations, I know a lot of social science use it, a lot in the physical and life sciences use this software. And so if you're interested in those fields, I would strongly encourage you to watch this video on how to download and use R to calculate these different figures that we'll be using throughout the semester. It does use some computer savvy because it does use a computer languaging system to assist with your analyses, but there's always scripts that you can run. So I would encourage you, if you're going to go into any of those areas, to actually look at this actual software right here. Okay. And so what I would like you to do, let's do this. Let me, in the announcement section, what I would like you to do. Oh, I got to get out of this first. I'm going to put a set of values. So I'll put it up here in announcements. Let's use. I like using these simpler numbers because then it's easier to calculate on your on hand if you need to. So what I would like you to do is use these values. Go to one of those tutorials that you're most comfortable with and try to figure out the mean and the sample standard deviation. Okay. All right, so I'll hit publish on this. Okay. And what I'd like you to do is tomorrow when you come into class, let me think about this. Have your answer available tomorrow. And then what we'll do is we'll do a poll, one of these polls on Zoom to see how many got it right, how many got it wrong, where we need to head with this idea, because I really need you all to understand the equation and how to work with these numbers a little bit and to use some of these softwares that are available. So, so let's do that for the rest of today and then bring those values back tomorrow and we will see how everyone did. Does that sound okay with everyone?
Sounds good.
Yes.
All right. All right. All right. All right, everybody go ahead and go do our activity for today. Thank you for coming. It's good to see you all here again this week. And I hope you all have a wonderful rest of your Monday and we will see you tomorrow.
Thank you.
I just wanted to quickly mention something. I'm gonna be missing Thursday's class